the homework problems? Any questions on the homework problems?
I don't think so. I was just trying to figure it out just a little bit.
Okay. All right, so I know there's only a few people here, but I was looking at the homework. A lot of people haven't even attempted the homework problems, but not a whole lot I can do about that. Um, so tomorrow we'll have our test. I wish I could delay it more because I feel like you need more time, but that's just the way the summer is. So I'll send you the test. If we have conflicts, we'll have to deal with it, but I'll send you the test by email around 11 o'clock. It'll definitely be before 11, sometime between 10:30 and 11. And you turn it in, email it, meaning email it back to me, scan it, take a picture of it, whatever you want to do. Let's say between 12:30 and 12:45, something like that. So the cutoff will be about 12:45. So I'm going to tell you what's going to be on the test. So this is test one. There'll be 5 problems, not necessarily in this order. One will be adding vectors. So a straightforward, given 2 or 3 vectors, find the resultant. Find the result. Go ahead.
Sorry, well, it's kind of like the lab we did.
Yep, sure will. And what you've done in the homework as well. I know it wasn't quite the same thing in the homework, but yeah, give you 2 or 3 vectors, and you find the resultant in component form, find the resultant in polar form. Number 2, this will be a displacement velocity acceleration problem. Meaning, kind of like the one with the train that I did the example of. So, you take a journey. You take a journey in one direction. You go to the north. You end up at some destination. Based on that, what's your displacement? What's your speed? What's your average velocity? Was there an acceleration? That type thing. Okay. Number 3. 1D motion problem. Kind of like the problem that we did with the car and the truck, something like that, where you have to find out where they meet, or, where they meet, that kind of thing. So a one-dimensional motion problem. Number 4. Some projectile motion problem. Okay, an object is launched at a particular angle. Where does it land? How far from the launch point does it land? All that kind of stuff. Yeah, so let's see. Number 5, circular motion. Simple. Okay. We haven't done a lot with or uniform circular motion. So a simple, straightforward, an object's rotating. What's the centripetal acceleration? What's the tangential velocity? What's the period? All those kinds of things. Go ahead.
Brooke wanted me to tell you that she was having some issues with her laptop, so she's trying to get back on, but she missed up topic 3 through 5.
Okay. Well, it'll be on YouTube tonight, so, or you can tell her, or maybe she can get back on. So I'm going to send this out in an email this evening, so tell her that. Okay.
Can you stand to the side for a second? Sorry, my computer turned off, so I didn't get to write down the stuff.
Yeah, I'll send this out in an email this evening. Plus, it'll be on YouTube sometime tonight. Is that okay?
Yeah, thank you.
Okay. I mean, you can hear me, right? So, adding vectors, that's number 1. Displacement, velocity, acceleration, that's number 2. Number 3 is a 1D motion problem. Number 4 is a projectile motion problem. Number 5 is a simple uniform circular motion problem.
Thank you.
Okay. We'll see how this goes. I mean, like I put in the original email that I sent you when we first got started, I'm much more concerned about you learning the material and getting a feel for this stuff than beating you down on the grades and things like that. I mean, this is all, personally, I can't imagine learning Physics 1 online, but I think this is a bit better with us being able to have these, synchronous meetings and so forth. But, we miss all that time where we, like before class, and we chat after class, and you come by my office and I see you in lab, and, it's just a lot of stuff that is missing, in my opinion. I was talking to Dr. Mariano about it on Tuesday, and so, I had to cut, obviously, there's some things that I'm not going to have time to cover. So we just do the best we can. I want you to learn the material. I want you to not feel stressed and all that kind of stuff. Just, anyway, that's my hope. All right. So, I know I already asked this, but maybe somebody came on late, but I was late. Are there any questions on the homework problems? Chapter 2, Chapter 3, Chapter 4. I went over all those in Chapter 4 yesterday, so if you haven't seen the YouTube video, you can watch that. I went over all the problems. Okay. All right, so we're going to start talking about Newton's laws. And really, everything that we do from this point on will be based on Newton's laws. Physics 1 is all about Newton's laws. A big part of Physics 2 uses Newton's laws. Okay, Physics 3, Newton's laws are the foundation of most all of physics. Mechanics, what we call mechanics, like we're learning, which would be sort of classical mechanics that we're learning in this class, it's the foundation for all the physics. Even quantum mechanics, you name it, it's got Physics 1 in it, okay, somewhere. So around, Newton was born in here's the history lesson. Newton was born in 1642. That was the same year that Galileo died. Galileo had done a lot of the work on falling bodies, accelerations. He did some really clever experiments with objects rolling down inclined planes and looking at accelerations. And this may seem simple, sort of, and they are simple ideas, but they're very, very far-reaching ideas. And, you know, Newton formulated his so-called 3 laws of motion, and he also formulated the universal law, or the law of universal gravitation, and he discovered the calculus. What didn't he do? I don't know. But, you know, Galileo and Newton are the real fathers of modern physics. Well, I'm saying modern, all of physics, really. What we think of as the things that we still use today. So, what got Galileo in so much trouble? Does anybody happen to know? I'm sure you do. Galileo was a rebel.
Rotation of the planets.
Yeah, Galileo said that the planets orbit the sun, and that was heresy. Catholic Church put him under arrest. They thought he was a pretty bad guy, and he eventually came into, or was brought into the church, and he recanted, okay? He said that, okay, I was wrong. However, as the legend goes, when he got up, he said, but I looked, I've seen it, you haven't, okay? So does anybody happen to know when the church, when I say the church, I mean the Catholic Church, does anybody happen to know when the Catholic Church finally said, okay, Galileo, you were right, the planets actually do orbit the sun? I know how the church finally acknowledged Galileo. Around 1990. So the church has a long memory. Okay, so it wasn't until around 1990 that Galileo was acknowledged by the church. Kind of strange, but Newton came along, and a lot of the things had changed by the time Newton came along. You know, Galileo was 1564 to 1642. So there were telescopes, there were people that were actually looking into nature and trying to figure out what was going on, and Newton was the leader, okay? There were others. So let's talk about Newton's laws of motion. He's got a bunch of laws, but these are his laws of motion. Okay? First law. Do any of you know what the first law is? I'm not going to write all these on the board. I'm just going to sort of put a title up here and talk about them.
Is it the object in motion stays in motion?
Yep. Yeah, it's called the law of inertia. That's the first law. Law of inertia. Okay. It says that an object at rest remains at rest, or an object in uniform motion remains in uniform motion, unless these objects are acted on by some external force. Okay? So we hadn't even talked about what forces are, but some external force. So it says that an object's velocity remains constant unless acted on by some external force. That's just another way to say it, meaning just what you said. An object at rest remains at rest. An object in uniform motion remains in that uniform motion. Okay, that's Newton's first law. So an object, let's say we're talking about a hockey puck sliding on, an ice rink. Once you give it that initial force and it's very, very low friction, you give it an impulse, it slides along in a straight line, okay? And it would just keep going like that, but it's acted on by friction, typically air resistance, all these other things, okay? To really see this first law, you need to be sort of in free fall, like up on the space station or something like that, and you toss an object, it just keeps moving uniformly, okay? That's the first law. Second law. Any of you know what the second law is?
Doesn't it involve acceleration?
It does. Newton's second law is really the payoff. That's what we're going to spend a good bit of our time talking about. It's the law that you can actually do calculations with. All right? So the second law is this force law, and it's F equals ma. I mean, that's it in a nutshell. Okay? It says that, well, let me write it. Let me be a little more technical. If you look at the net force acting on an object, so you sum up all those external forces, we're not looking at the internal forces. If we have an object like a rigid object, we're not looking at all those little internal forces that are going on inside the object. We're looking at the forces that are acting externally on the object. And when you sum up those forces, that equals the mass times the acceleration. Some professors and physicists like to write it like this. F net divided by, it's the same thing, it's just a different way to think about it, okay? That says that for a given force, if you have a large mass, you get a small acceleration. For a large force, small mass, you get a large acceleration, okay? This is really, in most cases, this is the dependent variable. We're acting on an object with some net force. There's a mass for the object, and the resultant is some acceleration. That's not always the case. We can work it either way. By knowing the acceleration and the mass, we can find that net force acting on an object, okay? You'll sometimes, this is a vector, by the way. We'll talk about forces in a minute, okay? We'll come back to forces and masses in just a minute. This is a vector. You'll also see it written as the sum of the forces is equal to the mass times the acceleration. So that means you sum them up as vectors. You sum all the external forces acting on an object as vectors, and that equals the mass times the acceleration, okay? All right, that's the second law. We're going to spend a lot of time working with the second law. What about the third law? That's the one you hear all the time in sort of everyday language. Third law? Anybody?
For every action, there's an equal and opposite.
Yeah. It's this equal action-reaction law, okay? This is really going to lead us into, later on, it's going to lead us into this idea of momentum and exchanges of momentum. But it says that for the third law, this is often called the action-reaction law. This one is sometimes tricky, okay? It's definitely a law. It definitely always is true, but sometimes it's hard to see. This says that forces always come in pairs. Meaning if I'm acting on an object with a force, say in this direction, there is an equal and opposite force acting on me in that direction. Okay? It's not like that I'm pushing the object and this force is just a little bit bigger than that reactive force. Mm-mm. They are exactly equal in the opposite direction. Okay? Whatever is creating the action and producing the force, there's an equal and opposite force acting on that body, that entity. Okay? Forces always come in pairs. There's never a single, I can't think of where you have a single force. Now, we're going to ignore oftentimes what's actually producing the force. Okay, say we have an object that is moving along or is being accelerated, box sliding on the floor, something like that. We may ignore what's happening to that entity that is actually producing that force because we're looking at just the forces acting on an object. But there's always that reaction force acting back on whatever is producing the force on an object, okay? So yes, it's this action-reaction. Forces are always pairs. If you have one force, there's always an equal and opposite force hiding somewhere, okay? This one, like I said, it pops up now and then. We're gonna put it in a little bit different language, and when we get to momentum and so forth, and we'll see how that works. So let's talk about force and the second law. Okay. Force. So tell me, what is a force? Just everyday, it doesn't have to be technical, just that thing which produces acceleration.
Could you repeat that one more time? I had a hard time.
Sure, yeah. What is a force? Just in everyday language, when I say a force acting on something. Go ahead.
A push or a pull?
Absolutely, it's push or a pull. Okay? There's some force, it's a push or a pull. Okay? You have we'll talk about different kinds of forces. These different types of forces create some kind of push or pull. Okay? So you can have forces like contact forces. That would be one type of force. That's like me pushing the door closed. I'm making contact with the object. I'm pushing on it. That's a contact force. You can have one of my lights went out. You can have like a tension force. That's like a rope, like a rope pulling on something. You have an object that's tied to a string or a rope, and you're pulling on it, you're pulling it along. That would be a tension force. Okay. Gravitational forces. We know that there is a force due to gravity. There's an acceleration due to gravity. That acceleration actually produces the force. Okay. That's for another day. As far as this relationship between this acceleration due to gravity and forces, but there's definitely this gravitational acceleration, and it produces a gravitational force. What else? Contact, tension, gravity. There can be electrical I'll just put E and M. That's for physics 2. You can have electric forces, magnetic forces, and so forth. So there's all kinds of things that can produce forces. But just in everyday language, you know, it's a push or a pull. Something's acting on an object, it's pushing it or it's pulling it, it's raising it, it's lowering it, somehow, okay? So, this is the idea of a force. Tell me what mass is. I'll talk about units in a second. What is mass?
Is it how much matter an object takes up?
Absolutely. It's the matter, it's the amount of matter in an object. Okay? The mass of an object does not change when you, let's say we take an object from the Earth and we take it up to the moon. Okay, we know that that force due to gravity will definitely change because the acceleration due to gravity on the moon is much different than what it is here on Earth. However, the mass of the object does not change. Okay, it's the amount of matter. And for many, many years, up until just a couple of years ago, this mass was based on the standard kilogram, which was a platinum iridium cylinder that's kept in France, in Paris. Okay, they have a way now, NIST, the National Institute of Standards and Technology, has a way which I haven't looked into very much, but I do know about it. They have a way to produce a standard mass without having this object that you have to get your hands on to compare things to. So this kilogram mass was in Paris, and I think there were 3 or 4 sister kilograms, as they called them, that one lived in the United States, one in Germany, one in Japan. I can't remember where all. So it was a big deal, to keep all these platinum iridium cylinders sort of accurate. All right, so mass is measured in kilograms. That's the standard unit of mass. It's a kilogram. It's 1,000 grams. All right. Kilogram is about 2.2 pounds. We're still on the English system, which is bizarre. We're the only, I think there's only 2 countries in the world that still use the old British system of pounds and inches and all that. Us and who else? Not the British, they're metric, okay? Back in the 1970s, the United States was going to convert to the metric system, and like everybody always does in the US, everybody has a big fit, and nobody wanted to do it, so it got voted down. Anyway, physics has always been metric, okay? You look in old physics text, you're going to see kilograms, meters, and all that stuff. All right, so mass is measured in kilograms. Force, since we already know that Newton's second law, this is for the magnitude of the force. A mass is in kilograms, acceleration is in meters per second squared. So this has units of kilogram, meters per second squared. Those are the units for acceleration in the fundamental units, kilograms, meters, seconds. This has a name, and it's called a kilogram meter per second squared is a...
Is it a Newton?
It's a Newton, yeah. Okay. That's a Newton. A Newton, the symbol for a Newton is just capital N. That's the SI symbol for newtons, capital N. So anytime we're talking about forces, we're going to be measuring those in newtons. There are other units for forces like dynes. A dyne is a gram centimeter per second squared. Like I said, a kilogram's about 2.2 pounds. Okay, so if you take a kilogram times the acceleration due to gravity, that's about 10 newtons. All right, so 10 newtons is about 2.2 pounds of force. You know, pound measure is actually a unit of force. So 10 newtons is about 2.2 pounds, something like that. Okay. What else do I want to say about this? Are there any questions about this?
Are we gonna talk about like the direction of forces and stuff too?
Yeah, sure. They're just vectors like any other old vector you meet. Okay. Let me see. Hold on a second. Yeah, so by looking at the forces acting on an object, we can calculate the acceleration. Once we know the acceleration, we can use all those things that we found out from 1D motion to calculate the motion of objects based on accelerations and so forth. All right. Let's see. So let's look at, sort of a typical problem. All right. Here's an object of mass m. I'm going to make this super simple. Here's some force acting on the object. Okay. I'll go ahead and put the vector symbol there. We know it's a horizontal force. It's a one-dimensional motion. Let's say that this surface is frictionless. Friction is another one of our forces that I didn't mention. Okay. So when we're working with these problems on Newton's second law, we always want to draw a free body diagram. A free body diagram kind of takes the object out of its environment, and we draw the forces that are acting on the object. Okay? So I know I've got this. I'm going to call this FA. This applied force. Okay? What are some other forces? This is a real object sitting on Earth on a flat surface. Okay. What are some of the other forces acting on the object?
Gravity.
Yeah, gravity is acting on the object this way. I'm going to call that FG. Any other forces acting on the object? Well, there is another force that is acting on the object. It's the force between the surface and the mass. That force is what we call the normal force. And I usually write it as F sub n. Some people call that the contact force, write it as F sub c or some notation. That's the normal force. It is perpendicular to the surface. Okay? So that is the action force, that's the reaction force, the normal force. All right. Anything else? I don't think so. Okay? Not concerned about any internal forces inside this object. Maybe this is a box full of little animals that are crawling around being shipped somewhere. I don't care. I don't care about these internal forces. This is a rigid object and it's sitting on this frictionless surface. Okay? So I really sort of, this is so simple, I've sort of drawn the free body diagram just on the object, but I like to take it and move it out of its environment. So here's M. I have the applied force, the normal force, and the force due to gravity. Okay? All right. So, analyzing this object, we always break it into the forces acting in the x direction, the forces acting in the y direction. Depending on what I call x and y, I can define my coordinate system however I please. But I'm going to define it just like this. This is x and this is y. That's it. Okay. Just like always. Oftentimes, we may want this coordinate when we start doing problems where that mass is moving along an inclined plane or a ramp. It's oftentimes easier to sort of tilt this coordinate system and deal with that instead of keeping that coordinate system flat or, perpendicular flat and dealing with this object moving at some angle in a coordinate system. We'll see how to do that eventually. Okay? Newton's second law says, I just wrote it down, but I'm going to write it down again. The sum of the forces acting on the object is equal to the mass times the acceleration. So we'll look at the sum of the forces in the x direction and the sum of the forces in the y direction. So in the x direction, we have just the applied force. I'm going to drop the vector symbol. So FA is equal to m times AX. That's the acceleration in the x direction. So if we knew the force acting on the object, the mass of the object, it's a pretty simple calculation. Maybe the force acting on the object is 100 newtons and the mass of the object is 10 kilograms. And you've got a 10 meter per second squared acceleration. Okay? In the x direction. Let's look at the y direction. So in the y direction, there is no acceleration. I know that from the physics. This thing is not raising up off the surface or falling through, okay? So in the y direction, I have the normal force is equal to the force due to gravity. Let me not write it like that, okay? One dimension in the y direction, F normal minus the force due to gravity is equal to 0. There is no acceleration in the y direction, right? No acceleration. So this says that the normal force is equal to the gravitational force. That's the third law in action. Okay. What is this gravitational force? If you have an object under the influence of the acceleration due to gravity, a massive object, then pretty darn simple. The force due to gravity, and I'm sure many of you know this, Fg simply equal to mg. I can write it as a vector, okay? We typically give the acceleration due to gravity, the vector symbol. I may not do that. We all know, I may go back and forth. We all know that acceleration due to gravity is down, okay? It's in the negative y direction, all right? So that normal force magnitude-wise, is equal to the force due to gravity. The force due to gravity is mg, so the normal force is equal to just mg. You got an object on a table, okay? Big, heavy object. It has a force due to gravity. That is the mass times the acceleration due to gravity. You've got to have a table that's strong enough that can produce that reaction force, okay, to hold the object at rest. Otherwise, the object falls through the table. Okay? You get a net force down, okay? The table's not strong enough and everything collapses. All right? So this is sort of the plan that we always have. We'll look at the forces acting on the object. Maybe I draw this instead of putting the forces here. We'll do a free body diagram to look at the forces more carefully. We always define a coordinate system. We take the sum of the forces in the x direction. That's equal to the mass times the acceleration in the x direction. Sum of the forces in the y direction. That's equal to the mass times the acceleration in the y direction. In this particular case, there was no acceleration in the y direction. The floor is nice and firm. It's holding the object at rest in y. Okay? Are there any questions on that?
I don't think so.
Okay. Thank you. Have you formulated any questions about the test?